So thank you very much for being here today, and thank you very much to the organizers for giving me the opportunity to talk to you about clones that are indeed digital twins of the local universe and that we can use for bias-free inference. So of course I'm going to explain all about that. So first of all, why are we all here? So we know that lambda CDM works quite well on overall, let's say, on the large scale. So for example, if you look at the angular power spectrum, so if you look at the angular power spectrum as a function of the angular size, you can see that if you don't have dark energy, dark matter, and baryons, like in green, you're not going to find back the baryonic oscillations. And the second thing, also, you can see that if you use lambda CDM, you are able to recover the cosmic web with filaments, its nodes, and voids, as we can see in the distribution of galaxies. But we also have some tensions. For example, we have the S8 tensions, where when you compare the value of S8, so the distribution of galaxy clusters in the universe, that you obtain with the CMB and the one that you can obtain with eclancing or counting galaxy clusters, you can see that the values are in disagreement. The same thing happened with the Hubble constant. If you compare the H0 value that you get with the CMB with that you get with the distance scale or the lensing of the quasars, then you see that you end up with different values. But my question is this really due to new physics? Or can this be due maybe to biases, some systematic effects? A little bit like these two guys who are looking exactly at the same thing, but not from the same point of view, and they end up with having different value. One see 4 bars, and the other one see only 3 bars. So let's take the example of S8. So it's the galaxy cluster count. So you can see that the value that you obtain with the Planck data is different from the value that you obtain when you count your galactic clusters. How you do that? It's basically that you are going to bin your galaxy clusters by bin of mass, okay? So you need to get their masses. So you see that this is in disagreement, but if I change the way I'm going to calibrate the mass of my clusters, maybe I can end up with having something that is less in disagreement. Why is that, and how can I do that, change the mass of my galaxy clusters? So everything comes to these equations where we assume that the galaxy clusters are in hydrostatic equilibrium. Basically, the pressure of an intracluster medium is exactly the opposite of the gravitational potential that you have in your cluster. Plus, you assume that the symmetry of your cluster is perfectly spherical and that there is no pressure other than that, so no turbulent, no magnetic pressure, so you can get the hydrostatic equilibrium mass. That is the last blue line. And you can link this hydrostatic equilibrium mass to the total mass of your cluster, that is the dark matter, the gas mass, and the star mass, thanks to this relation here where you have 1 minus b, that is hydrostatic mass bias. But how can you get this 1 minus b? The only way to get it is from cosmological simulations, okay? The problem is when you go to cosmological simulation to get this value, you can see that it's completely disparate, right? Depending on the simulation you are going to use, you can see that I can end up with very different values from 0.6 to 0.8 to 1, etc. So it depends on what you put in your simulation. So given that you have all of this variety of possible value, how can you actually choose one to apply to all your cluster? This is not very clear. So all that to say that when you are measuring cosmological parameter, you have your value. You have an uncertainty that is due to let's say, the general uncertainty, so that you can reduce thanks to your number of measurements, your number of observations. But you can also decrease thanks to the sensitivity of your instrument, the tools, the method that you are using. This is the precision. But you have a second one that is due to the systematics. So here I have my uncertainty due to my measurement, but not my systematics. And if I want to have the one due to the systematics, I can go to cosmological simulations, but not just one. I need several of them to see how the value changes depending on one simulation to the other. But there is also one way to completely remove the systematic by using a typical, let's say, atypical cosmological simulation that are called constraints. Okay? These constraint simulations, what are they and how can they help us actually remove the systematic effects rather than just estimating its value? So first of all, what is a standard cosmological simulation? How do you get a standard cosmological simulation? You start with this part of the universe that is at more than 13.7 light years away from us nowadays, okay, that we observed when it was 380,000 years old. So this is what we get from the CMB. If you assume the universe to be homogeneous and isotropic, then you can say that the power spectrum of this part of the universe that is very far away from us should be the same in every other part of the universe when it was also very young. Assuming also that the initial density field is a Gaussian, then you can say that any initial density field, delta, is actually the square root of your power spectrum times a white noise. And when you do that, then you get initial conditions of whatever part of the universe, okay, completely random part of the universe that you can run forward, and that's what gives you a standard cosmological simulation. Now, we don't want to do that. What we want to do is to change this delta to get initial conditions of the local universe, not whatever random part, but the part of the universe we live in. How was it when it was young? So when I run the simulation forward, I can get the local universe. So I'm not going to explain all of it, how to do it, but we can discuss it afterwards. Let's say that I've done it. I have constrained my initial conditions, and here I have these initial conditions that I can run forwards. So it's an example of this type of constraint simulation here that you see on your left before we run it, and then we run it forwards in time, and we end up with the large-scale structures of a local universe nowadays. Just to convince you, let's compare it. So here you have the XY supergalactic plane of the local universe. So all these black dots are galaxies that we observe. You can clearly see the zone of avoidance because of the Milky Way dust. You can see all these big concentrations, Shapley, Coma, tertiary species. You can see also that it's not corrected for the finger of God. So you can see that it's elongated along the line of sight. Of course, I didn't say that we are in the center just by observation of the local universe. And on the other side, you can see a slice of the simulation, exactly the same. We are in the center of the box, and we are looking at the structures. So let's try to compare it a bit. I highlighted a few high-density regions in the simulation and in the observations. So you can see, for example, the Virgo cluster and all of these large structures quite close to the center of the box, and of course, of observations. You can see Coma at the top. You can see Shapley on the left side, and you can see, for example, species on the right side. Okay, you can also look at the voids, because we have seen the high-density part. Let's look at the low-density region. And I highlighted two voids, and you can see that we also have the two same kinds of voids. Okay, so now that we have these large-scale structures that correspond to actually the local universe, we can also look directly at the clusters one by one, simulate them with high resolution, and compare observations and simulations again. So here what you have, it's a simulation of a Virgo cluster, high resolution. So here you have the resolution at the bottom. It's effectively 8,182 cube particles, and the size of the cell is 0.24 kiloparsec per H. In this simulation, you also have feedback, as it's very important in cluster, like supernovae and AGN feedback, and we use the Planck cosmology. So what you see on the left side is the superposition of dark matter and gas in the cluster. You can see the radius, the velocity radius, and you can see at the center of this cluster, there is M87 counterpart, where you can see superposition of dark matter, gas, and stars. So what the student did is that he took this simulation and tried to see what kind of projection effect we can have on the hydrostatic mass bias that you can measure. So basically, he looked at the simulation from different points of view. You can see that you can put yourself in the direction of the main filament, that is in blue, but you can also put yourself perpendicular to the main filament, either in green or in gray. And you can also put yourself in the line of sight, actually, just like you were in the Milky Way looking at the Virgo cluster, and this is in red. Okay? So, and then I took the same color for the quadrant of your different images. So you can see that the line of sight, for example, how we can see the Virgo cluster from the Milky Way is on the top left side. So what you see is that, first of all, just looking at this map, it's very different depending on which direction you are looking at your cluster. So of course, what you are going to measure is going to be different because you are not seeing the same thing. So what you can measure now, because remember, there is a link between the pressure and the mass of the cluster, of this hydrostatic mass bias, you can measure the profile of the pressure in these different maps. And what you can see is that these pressure profiles are very different depending on how you observe your cluster. And unfortunately, the most different one is the one in red. It's our line of sight. Why is that? It's because there is a group just in the line of sight between Virgo and us that actually is perturbing the profile we measure, just because by projection it ends up being on the map where it shouldn't be. You can also see that there is an effect of the AGN feedback and that there is an effect of the matter that is accreting along the filaments into the cluster. This has a repercussion on the 1 minus b value that you get, so the hydrostatic mass bias. So you can see that depending not only on which direction you're observing your cluster, but also at which distances. So if I look at R500 or R200 or R virial, you can see that I end up with having very different values of 1 minus p, just for one cluster. So imagine when you have all of your cluster and you apply the same 1 minus p value. So just to say that at the beginning I showed you all the values that are obtained in different simulations and that we apply to the galactic cluster, but you can see that none of these actually apply just to the Virgo cluster. The Virgo cluster ends up having very high values, and depending on the direction of observation of this cluster, the values are very different. So it's not really a good approach to say I'm going to choose the same value for all the clusters. We have to go really more like deeply into individual clusters to choose this value. Second hypothesis that we said, okay, it's spherical. I'm not going to go into that one, but of course you know that it's not spherical, but this is for another talk. But I want to go to the pressure. Is it really true that there are no other source of pressure other than thermal pressure in a cluster? Is there not, like, for example, turbulent pressure? So another thing that the same student did is that he looked at the velocity map. So here you can see the temperature on the right, the XY map of the same galaxy cluster. And on the other side, you can see the velocity field, so red and blue, depending on whether the velocity field seems to be coming towards you or the gas seems to be coming towards you or going away from you. And what he did is that he he did some slices perpendicular to this filament at different distances from the cluster center to measure actually the different components of the velocity field. And doing that, here you have a different map cut transversally to the filaments. And you can see that light red to dark red and dark blue to light blue is going toward the cluster and then away from the cluster again. And you can see the different, the ratio between the different components of the velocity field, so the compressive component and the solenoidal component. What you can see is that when you are far from the cluster, the ratio of the two is quite high. When you are coming towards the cluster, the ratio of the two is smaller. Meaning that basically when you are far from the cluster, your velocity field is more like compressive, and the closer to the cluster you are, the more it starts to be solenoidal and to turn around. Doesn't mean that there is turbulence, but it seems like it's high probability that there is turbulence when you go close to the cluster. Okay, so I think I'm still okay on time yet. Okay, so that was one example of what you can do with that cluster thanks to this big digital twins that is a clone of a local universe. Of course, you can do other things on smaller scales, for example, with the local group, but also on other aspects, like looking at the propagation of cosmic rays, at the connectivity of your clusters, how also this can distort the Hubble diagram. You can look at local web and the distribution of the galaxy cluster in general. You can look into the zone of avoidance to see if you have very large structures crossing the zone of avoidance, and many other things that we are actually looking at, like ionization as well, and so on. So if I summarize everything I have said, we have standard cosmological simulation to have full uncertainty on our cosmological parameters. Remember, there are two parts. You have your uncertainty that you can get from your measurements, but you also have a systematic that you need to take into account. And this you can get from standard cosmological simulations. But if you want to remove them or actually reduce them, the only way to go is to use constrained cosmological simulation, so you exactly have what you observe in your simulation. So you can take care of all the biases. And clones are one example of constrained cosmological simulations. Didn't show that, but actually it's valid down to, it's valid down to the cluster scales. You have seen that because I showed, for example, the cluster, but also it has also the very small scales, like, for example, the Milky Way and Andromeda. Just to tell you. So I showed the large-scale structure with dark matter. I showed one zoom on one cluster, the Virgo cluster with hydrodynamics. And now we have this big simulation with all the clusters and hydrodynamics, so the full box that is coming in. I'm actually writing the paper where you will have all the clusters of a local universe with hydro and supernovae, AGN feedback, and so on. So for example, here you have a few examples. You can see Virgo, you can see Coma, you can see Shapley, actually the main cluster of Shapley, etc. So I pointed a few of them. And what you can see here is the velocity field. So basically, this is in supergalactic coordinates. So red means that it's going away from you, and blue means that it's coming towards you. So this is coming up, but all the other twins are already available. This one soon as well. And maybe you are the next user. Many thanks.
Okay, so questions, comments?
Thanks. I was surprised to see those bias values greater than 1 in your simulation, which means that your recovered mass is actually greater than the true mass, which is not what we typically expect. So can you comment on that?
Yes. So actually, it's because in the simulation, the Virgo cluster is not relaxed at all. So what happened is that there was a merger between two big galaxies almost at the end of the simulation. And they have two massive black holes, and these two black holes merge because the two galaxies merge. And it did a huge AGN feedback that actually heat up the core of your cluster, and then it just changed all the turbulence, everything, and then increased the hydrostatic mass bias that we get because there is no equilibrium at all at this point.
Thanks. I have yet another question on this plot. So I would like to ask, why is the value of 1 minus b equal to 0.6 taken as a reference if all of the simulations show? And why isn't one of these simulations taken as a reference instead?
Yeah.
Because they seem quite consistent.
No, it's an excellent question, and it's because I didn't say it. Sorry, I forgot about that. It's not the reference 0.6, and sorry again, I didn't say it. It's the value that you should get if you want to have the same S8 value as the CMB. So if you want to get the same S8 value as you get with CMB data, you should find in your simulation an average value of 1 minus b that should be 0.6. And then you will end up having exactly the same S8 value of the two measurements.
So why are there differences between the hydro simulations? Is it because they're seeing different clusters, or is it something to do with the underlying physics that they're assuming? Or is it their cosmology is different?
The main thing here, you can see different colors, and the main thing between these different colors is actually the feedback that they use within it. So for example, the one with the largest scatter, if I right remember, there is no feedback. So no supernovae, no AGN feedback. For the other two different colors, one has supernovae, the other one doesn't have AGN feedback. And also it really depends how we implement it. For example, some have isotropic AGN feedback only, others have jet AGN feedback, and really depending on all your subgrid physics, it can change completely your result. So okay. That's really what's going on here, bionic things.
Right, so now a follow-up question. So how would you go on to do a cluster analysis, given what you talked about?
So the next step that we would like to do is that now that we have this simulation that really resembles the clusters, it's really to calibrate properly the subgrid physics model thanks to the observations. Because now we can really do one-to-one comparison. So we are not going to calibrate the subgrid physics model overall, globally, but really on a one-to-one cluster. So you can check that if it works for one, it works for the other one, and not just overall, but like really,
okay.
Like not choosing one parameter that works best, but really the optimal parameter.
So you will have to have resolved all the clusters,
yes,
like exactly in your...
Exactly.
Yeah.
And that's what we are going to do with the big simulations that we have. First, check that the subgrid models that we currently have manages to reproduce exactly all these observed clusters, and if not, how we can actually change this parameter in the subgrid physics model. And maybe we are also, well, maybe no, I'm sure we are missing also some subgrid physics still.
Thank you.
Very nice talk. So I was wondering, earlier this week there was something similar. There was this Manticore project also having presenting. So I was curious as to how does your clone, differ or compare with this other twin? Yeah.
Yeah, exactly. So the main difference is the constraints that we are using for this Manticore project. What they are using is the distribution of galaxies at redshift 0. So basically how the density of matter is distributed. So while what we are using is really the peculiar velocities of the galaxies. So we are using the motions to constrain the simulations while they are using the distributions. And then one main difference is that while they indeed constrain maybe much more the distribution, the spatial distribution, we constrain much more the velocity field. So we constrain much more also with time what happened to halo and how it forms. So it's one of the main differences.
Thanks. But you have about the same volume then?
Yes, it's almost the same volume. Yeah.
Thanks.